All right, let's talk about stoichiometry. Stoichiometry is just, it's the study of ratios. And so we just compare the quantity of one thing to the quantity of another. That's all stoichiometry is. And so in chemistry, we're going to begin talking about stoichiometry by looking at what's called mole-to-mole stoichiometry. Okay, and so this is all based on having balanced chemical equations and the correct coefficients where they need to go in a chemical equation. So the first thing we want to talk about here is what does a balanced equation actually tell us? So when we balance a chemical equation, what we've tried to do is follow the law of conservation of mass so that all of the reactant atoms are represented as product atoms as well, and we do that through that bookkeeping method of balancing equations that we already know how to do. So here is a balanced chemical equation. We can see our coefficients 4, 3, and 2. And let's talk about what this was really telling us. So the way we learned this initially was that these coefficients would multiply by any subscripts in these formulas, and that would tell us the number of atoms of iron and oxygen and whatever. So to be honest, though, it's probably not as good to think about working with 4 individual iron atoms and 3 molecules of oxygen to make 2 units of iron 3 oxide. That's probably not really realistic. I mean, getting a hold of 4 iron atoms at a time is a pretty tough thing. So what we want to do now with these coefficients is think of them as a number of moles. So that's 4 moles, 3 moles, and 2 moles here. And what this reaction tells us now is basically that to make 2 moles of iron 3 oxide, it requires 4 moles of iron to react with 3 moles of oxygen gas. And that's the ratio part of this. So it's a 4 to 3 ratio to make 2 moles of iron 3 oxide. So we'll work with these coefficient numbers primarily here and look at the ratios that exist between them. So the coefficients can give us this thing called the mole ratio, and so we're only going to look at 2 of the parts of the reaction at one time. So in this reaction, we can say that the ratio of iron to oxygen gas is a 4 to 3 ratio. Okay. Iron to iron 3 oxide here is a 4 to 2 ratio, which is the same as a 2 to 1 ratio. You can reduce that down if you like, although it's not totally necessary to do that. The oxygen gas to iron 3 oxide, this is a 3 to 2 ratio. And then oxygen to iron is 3 to 4. Kind of the opposite of the iron to oxygen. So we're only going to look at 2 things at one time in this first part of stoichiometry. So these ratios are important to understand, though. And so let's do some practice problems. We'll work with this same equation. So here it is, and here's the typical kind of easy question that you would see on your homework and on your quizzes and tests and stuff. How many moles of iron 3 oxide are produced if 9.52 moles of iron react with excess oxygen gas? So the first thing you might be wondering about is what does excess oxygen gas mean? Well, it just means that there's plenty of oxygen gas around. Oxygen is something that's usually an excess reactant because maybe this reaction's taking place out in the atmosphere somewhere where there's plenty of oxygen. It just means that there's way more oxygen than is necessary to react all of the iron that is present in the problem. That's how an excess reactant works. So the excess reactant really doesn't play any part in the math that you're going to see. So just knowing that it's excess means that there's plenty of it, you're not going to run out of it, and all of the iron that you have from the problem is going to react. Okay? So to do a problem like this, we need to define a couple of things. So we're gonna look at chemical A and chemical B, and really in a stoichiometry problem, we're only looking at two chemicals at one time anyway. So one of the two chemicals is chemical A, the other is chemical B. But starting with chemical A is the chemical in the problem that you're starting with and that you know the amount of. So chemical A in this case would be iron. The Fe is the chemical A because we know how many moles of it we're starting with. Okay, that's important to really understand how these things are defined, because we're going to use chemical A and chemical B in some upcoming stuff. So A is the one that you have an amount of from the problem. Okay, chemical B is the chemical that you're asking about in the problem. So the question is about iron 3 oxide. How many moles of iron 3 oxide? So that is chemical B, and this is chemical A. All right, so A is the one that you know the amount of to begin with, and B is the compound or chemical or element or whatever that you're asking about. Okay, so here is how this gets set up. We're going to use very simple dimensional analysis to answer this question. And the way that we set it up is the given moles of chemical A is going to go in this upper left. And then this part here, this is the mole ratio. And the mole ratio comes directly from the balanced chemical equation. And so we have to look to the coefficients in the balanced equation to figure out what numbers are going to go there. So we've defined chemical B as the iron 3 oxide, sorry, I keep saying that. And then chemical A is the iron. Okay, so those are the coefficients that we're going to pull out of these balanced chemical equation and do the math. And here's what that looks like. So we have the question was, again, how many moles of iron 3 oxide are produced if 9.52 moles of iron, that's our chemical A, is reacted with excess oxygen. So that 4 comes from that number right there, right? That is the coefficient of our chemical A. And the 2 comes from chemical B's coefficient, and that is the chemical that we're asking about. We're asking about how many moles of iron 3 oxide are produced. Okay, so now it's a very easy math setup. It's 9.52 times 2 and then divided by 4. So let's we can hammer that out here. 9.52 times 2 divided by 4, and that gives us a 4.76. And then, think back to what the question is asking you, how many moles of iron 3 oxide. So this is moles of Fe2O3. All right, so it's not very challenging. I think the chemical A and the chemical B scheme makes it really pretty easy. Let's do a couple other problems just to solidify all this. We'll work with the same equation just for simplicity's sake. How many moles of oxygen gas are needed to fully react with 32.86 moles of iron? And again, we're only asking about two chemicals in one problem here, so we just have to define which one is chemical A and which one is chemical B. And so here chemical A is going to be iron because we know how much of it starts. So iron is chemical A. And then we want to know, we're asking the question about oxygen gas, how many moles of oxygen gas. So this is our chemical B. Okay, so we're just going to set it up the same way we did the last one, where we're going to take our given grams of A, sorry, not grams, moles, given number of moles of A. So this is 32.86 moles of iron. And then we're going to put in our mole ratio, which again comes right from our balanced chemical equation. So we have defined iron as A, so that's a 4, and we've defined oxygen this time as B, so that's a 3. Okay, so again, it's just really simple math. 32.86 times 3, and then divide that product by 4, and we get our final answer, 24.65. moles. And the question again was how many moles of oxygen gas. So how many, that's that many moles of oxygen gas. Okay, easy. Mole to mole stoichiometry is a piece of cake. It can get harder than this, and that's for later on. But with any of these problems, it doesn't really matter how it's asked. The same chemical A and chemical B kind of scheme is gonna hold true for these. So it doesn't, you're not always asking about the production of a product or something like that. Like in this question, we've actually got a produced amount of iron 3 oxide, and the question is how many moles of each of the reactant were used. And so in this case, our starting amount of iron 3 oxide, that makes it chemical A. So chemical A is our product in this example. So we can do this, and the question is asking how many moles of each reactant were used. So this means we have to do 2 problems, one for the reactant iron and then one for the reactant oxygen. So let's just do them both. So we're starting with our 26.8 moles of Fe2O3. So how many moles of, which one's first in the equation? Yeah, iron. Iron comes first in the equation, and I always just sort of work from left to right when I do this. So I'll do the iron answer first here. And so again, just use the mole ratio. So again, the coefficient for chemical A was a 2, and the mole coefficient for iron was a 4. And you can reduce this if you want to a 2 up here and a 1 down here. It doesn't really end up mattering in the long run. I usually don't do that actually, but you can. So 26.8 times 4 divided by 2 is 53.6. So 53.6 moles of iron must have reacted. And now we can look at oxygen as well. So here's our O2 problem down here. So we're going to start with our same chemical A with the amount here, and that is 26.8 moles of Fe2O3. And the coefficient of iron 3 oxide again was a 2, and the coefficient from oxygen from this equation is a 3. So now we just 26.8 times 3, and then divide that by 2, and that gives us 40.2. So this is 40.2 moles of oxygen gas. Okay, so those are our 2 answers. And actually, you probably could have gotten this answer by using, if you wanted to compare the amount of moles of iron to the moles of oxygen, you could have done it that way too. There ends up being a couple of different ways to go about this, but this is a really fail-safe way that hopefully makes good sense to you. All right, so that is mole to mole ratios, mole to mole stoichiometry.